Yep.
But technically they're the same. The top one's just calculated.
No, see, the wrong word there you used was technically. Because technically, they're not the same.
But if you calculated the bottom one,
I'm
then technically...
going to tell you. On this calculator screen, you did the square root of 150 and it filled up with no repeatings, yes?
But...
Just don't be a kid and answer a yes-no question. When you punch the square root of 150 into your calculator and you hit equals or enter and the whole screen fills up with those digits, right?
Should that be irrational then? Because it doesn't have...
Is that what happens? Yes. And if you write out those digits, 247444871, I wrote them right there, yes? Did I stop writing?
Yeah.
Yes. So as soon as I stop writing, it is a rational number because it has ended. But does 150 have a square root? No. No, that is the square root, as much of it as will fit on your calculator screen.
But isn't there more beyond the calculator?
Yes, there is. Which is why when I write it out, it's rational because I stopped.
What if I wanted to stop at 448? Can I do that?
It would still be rational because you stopped. And it keeps going. This right here is irrational because if we had an infinitely long calculator screen, it would fill out to here without repeating. Understand? Your calculator rounds the square root of 150 off to the end of its screen.
So because that one's not rounded or like calculated, you're just like looking at it as it is, so then it's irrational.
Yes.
Because it doesn't go on forever.
Yes.
But the calculated version is rational?
Yes.
Is that for like a lot of equations?
Well, that's why I'm saying I want you all to let your calculators go. Right? You have to stop believing your calculators. You have to learn math, right? Your calculator cannot do the square root of 150 because there isn't one.
How do I tell just by looking at it then?
If the whole screen is full and it doesn't repeat.
No, by just looking at square root of 150.
Okay. That's what we're about to move into. Okay? That's why this question was here. That's why I'm stopping you at just, is it rational or irrational?
Oh, this wasn't homework? Like this doesn't have to be done?
Yeah.
Wait, we didn't have to do it?
Yes, you did have to do it.
Okay. I thought we got to choose it.
No. All right. Anything else from here? Edward.
I had trouble understanding these.
How do you write a rational number that isn't an integer?
I'm going to do his first, and I'll come back to you. Number 18, you had this. So use a calculator. Now, Paige, does 5 have a square root?
It's like 2.5.
It doesn't, right? Because 4, square root of 4 is 2. And then the square root of 9 is 3. So there's nothing between 2 and 3. 5 would be in the middle there, so it doesn't have a nice perfect square root, right? So you know, because it's a little number, that it's irrational, right? So to do this on your calculator, you have to remember BEDMAS, yes? And what this is saying is that whole number, I shouldn't have said whole, that entire expression is then divided by 2. So how do I tell my calculator to do that part first? I have to put brackets in it. So to punch that into your calculator, you would have had to do, and I'll bring a calculator up on the screen, bracket 1 plus the square root of 5, close the brackets, then divide by 2. And it will give me the answer that I seek. Now, I said I wanted it to the nearest tenth. It is so appalling to me how badly you people round things off. You're bad at it. This answer is easy because it rounds down. What is this answer to the nearest tenth? 1.6. Now, at some point in this course, we will be doing measurement stuff, trigonometry, and I will say round it to the nearest hundredth. And at least half of you will say this is 1.61. At least half of you, because you don't know how to round. Don't make me do a lesson on it. Okay? Now, Edward, you good? Okay. Paige, you want to know how do you write a rational that isn't an integer?
Yeah, because an integer isn't that all the numbers?
An integer are all numbers. Rationals are fractions. So 3/4 is a rational number that's not an integer. Okay?
But isn't that just two integers that we're talking about?
That's what makes a rational number. Any integer divided by another integer.
But an integer is still an integer.
No. An integer divided by an integer is a rational number. Because that's not addition.
Any integer divided by another integer is rational.
Yes. Yes. As long as the denominator isn't 0. Because that's what we wrote right here, remember? Rational numbers, x over y, as long as x and y are integers. But y can't be 0, because we can't divide by 0, because that's infinity. And it doesn't exist. In our notes, under rational numbers, when I explained what a rational number is.
I'm learning. I did copy it all down. Just page didn't write down.
All right. So, we're good? Okay. Please turn your pages, your books, to page 22. Factor trees. Now, if you call your minds back to about grade 5 or 6, you've done these before. And when you did them before, chances are your teacher stopped as soon as you learned how to do them. So I will call your minds back to the day she wrote a 12, or he wrote a 12 and said, what are some factors of 12? And you said, what's a factor? And then they reminded you, those are any two numbers that multiply together to equal a product. My product is 12. What are any two numbers that multiply together to make 12? 4 and 3.
Actually, can we start with 6 and 2?
No, because we've already started with 4 and 3, because it doesn't matter what we start with, right?
I just personally feel like
It's okay. And then, Carlo, what would you do next?
2 and 2 under the board.
You would make that 2 and 2. Right? And Mrs. Bag-Crumble would say, good job! And then she would give you another number. And you would do it again. Right?
in factor trees, don't you have to put all of the factors though? Because 6 is in there.
Yeah.
Oh, never mind.
6 is in there. 2 times 3. All right. Then she would give you another number, and you would do it again, yes? This time you might go 9 and 3 and 3 and 3, right?
Wait, so 9 times 3 is 27.
3 times 3 times 3 is 20. Yeah, 9 times 3 is 27, yes. Okay? Then she might give you another one, 36. And you might go what?
6 times.
You might go 6 times 6. And then you would go what? 2 times 3 and 2 times 3, yes? You've all seen some kind of math construction like this, yes? Maybe your teacher did them horizontally. I don't know, right? I don't know. I wasn't there. But you've all seen something like this, yes? And all of you should remember that when you finish these trees, you were done, right? And you moved on to the next thing. And that was what, 4 or 5 years ago, yes? Well, here we are 4 or 5 years later, and we're going to take this thing that you learned 4 or 5 years ago and haven't touched for 4 or 5 years, and now it's going to become very, very important. Now, is that a smart way to teach it? No, of course not. But that's what we're stuck with. So, we are going to use these factor trees to do a whole bunch of stuff in math. But the first thing we're going to do is talk about prime numbers. What are prime numbers? Somebody knows. Abby.
A number that doesn't have any factors.
It's only got two factors, itself and 1. And prime numbers are very, very powerful because they are completely random. There is no pattern for them. You cannot predict when they happen. The most recent prime number discovered was something up in the billions, which is crazy that a number that big can have no other factors except itself and 1. And it is true. When the aliens come, they will talk to us with prime numbers, I believe. They're important in code breaking. They're incredibly important in data management. Okay? They have a real life use, but it's a little beyond Math 10. So for our purposes, they're powerful numbers because they only have two factors. Is any number with only two factors. And those two factors are 1 and itself. Now, what do you feel is the most powerful prime number?
7,
No.
5,
Wrong.
3, 1.
No. 1's not a prime number. 1 only has one factor. 2. Why is 2 the most powerful prime number? It's the only even number. 2 is the most unique. Which I know is stupid to say most unique, right? Because if something's unique, it's unique. Right? It can't be more unique than something else. But anyways. So 2 is a very powerful prime number. So what we're going to do now, before we do anything, we're going to bring ourselves back to grade 6, and we're going to make 2 factor trees for bigger numbers than you ever did in grade 6. But you all know how to do it. Okay? So everybody, without talking out loud, without yelling an answer, don't tell me, write down any 2 numbers that multiply to 54. Just take a second and write it down. I am betting that almost all of you are going to write the same 2 numbers.
27, 2.
That is not what I would have bet. Carlo, 9 times 6 is what I'm betting almost everybody did. And that's cool. You could also have done 18 and 3. You could also have done 27 and 2. Okay? So everybody put in their first branch. I'm going to use 18 and 3. You do whatever you add. If you were like Carlo, you have 9 and 6. That's cool. Doesn't matter. Now, is 3 a prime number? Yes. So we stop our branches at any prime number. Is 18 a prime number? No. So for me, I'm going to break 18 down. You are going to break down whatever you have on your branches. So I'm going to break down 18, and I'm going to go 2 and 9. 2 is prime, so I'm going to stop. 9 is not, so I'm going to break it down again to 3 and 3, and then I'm going to stop. Everybody cool?
Yes.
And no matter how you started, you are all going to end up with 1, 2 times 3 times 3 times 3. Right? 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54. Now, would we ever write it that way? Like, would math people write that many 3s? What would they write? 2 times 3 cubed. Everybody cool? Do the same thing for 162. Since it ends in 2, what would be the logical one to start with?
81 and 2.
It would be 2 and 81, because it's an even number, so we know it divides by 2. 2 is prime, so we circle it. What is 81? 9 and 9. 9 and 9. Either of them prime? No, so we break down again. 3, 3, 3, 3. Prime, 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 prime. What is that? 2, 3 to the power of 4. Is everybody cool? We have done nothing new, right? We've done division. We learned that in grade 3, right? We're cool, yeah? Everybody's cool, right? You can all draw these in your sleep, upside down, left-handed, backwards, underwater, while a great white shark is chasing you, and you're a little hungry because you ate lunch too long ago. You all could do it, yeah? Okay. Now, unlike grade 6, we're going to use this information to do something. Okay? The first thing we're going to use is to find a greatest common factor, or GCF. This is extremely important in making math simpler and easy to work with. Okay? When we use greatest common factor is when we are simplifying fractions. So, let's do that. A greatest common factor, GCF, is the largest factor that's shared by a group of numbers. All right? So, do we have a group of numbers on this page? 54 and 162. Two of them, right? You find the GCF when you have prime factorization. That and that is prime factorization. Because do you see any numbers highlighted in yellow that are not prime numbers? No. So when you get to prime factorization, you can find the GCF by counting the common, I'm going to highlight common, the common factors by the lowest exponent. So, in 54 and 162, is there a 2 in both of them? Is 2 common to both of them?
Yep.
Yes. What is the lowest exponent shown by a 2? 1. So, there's a single 2. Agreed? Is there a 3 common to both of them?
Yep.
Yes. What is the lowest exponent of 3? 3. So that means 54 is the greatest common factor of 54 and 162. And that makes sense because 54 times 1 is 54, and 54 times 3 is 152. 62. Everybody cool? All right. Now, next, this we use for simplifying. That's what we use the greatest common factor for. The lowest common multiple, LCM, is the smallest number that shares your whole group as a factor. Now that's a little cumbersome to read, but you already know this. Lowest common multiple, you know it as lowest common denominator. Okay? You've all done that before. I'll take a quick second just to remind you. 1/3 plus 1/2. What do we have to do?
Times the 3 by 2 and times 2 by 3.
Times 2 times 3, 6. Because 6 shares 3 and 2 as factors. Okay? You've all done that before. So we apply it here in another way. Again, we use prime factorization just like before, but this time, instead of counting the common factors, we count all the factors by highest exponent. So, we have to count them all. So, once again, is 2 a factor that we have to count? Yes. What's the highest exponent visible to 2? 1. So it's just 2 to the 1. Do we count 3? Yep. What's the highest exponent that we have for 3? 3 to the 4th. So 2 times 3 to the 4th is 162, which makes sense because 162 times 1 is 162. So 162 is a multiple of 1. And 54 times 3 is 162. 54 times 3 is 162. So that means 162 is a multiple of 54. 54, 108, 162. The same way that we find common denominators. Now the problem with finding common denominators is back when you were kids, the teacher always gave you pretty small fractions, right? And they worked together real well. 4 and 5. What's the common denominator? If I had 1/4 plus 2/5, what would you say is your common denominator? 20, right? And most of you probably found these by skip counting. You went 4, 8, 12, 16, 20, 24, and then you went 5, 10, 15, 20. Oh, there's your pair. That's probably how most of you learned to do this back in the day, yes? Damn it! But that is probably how most of you learned to do this back in the day, yes? You listed. If you didn't actually write it down, you thought in your head. 4, 8, 12, 15, 20, 5, 10, 15, 20. Oh, 20, got it. Okay? But of course, like we talked about yesterday, numbers go up to infinity, right? And sometimes you have bigger numbers than you can just work with in your head. Yeah? That's where this comes in. Okay? It's going to take a moment for this to restart. I don't know why it's being so bad wordy, but we'll just take a second for it to work. But at the bottom of page 22, you now know the GCF and the LCM of 54 and 162. The GCF is 54, and the LCM is 162. Now, we're going to practice this some more on the next page right now, but I'm going to remind you that it does not matter how many numbers there are. It does not matter how big the numbers are. You follow the same rules. Page.
Would it make sense if the GCF was 162 because it's greatest?
I was just actually going to ask about that. I was going to say, is everyone cool? And somebody always says, how can the greatest of anything be smaller? Exactly what you said. Because factors are parts, right? So, for example, if my screen ever lights up again, I'm going to have to. Oh! Technology, right? So, factors are parts of the whole, right? So if I have 20, the factors of 20 are the smaller numbers, right? And the factors of 16 are the smaller numbers, right? So 20 has all the way down, 10 times 2, 5 times 4, right? So 4 is in the group here, because 4 times 5, right? And 4 times 4 is 16, so 16 shares a 4. So it's the greatest common factor. It's the biggest of part. You with me? And the lowest common denominator is the lowest of when we go up. Okay? I know it's weird. I don't like the nomenclature either, but that's what we use.
So instead of going all the way down and finding the GCF, we just do the one that comes first?
You do the highest number. We're going to do one right now, and you'll see. Trust me. You're going to be good. So let's look at number 1A here. I have two numbers, and we need to get the prime factors to find the GCF and the LCM. So first thing we need to do is get the prime factors. There's lots of ways to get the prime factors. Most of you are familiar with factor trees. That's why I use factor trees. If you have another way to do it, you're from another country, you've done math somewhere else, in another province, whatever. Maybe you got a different way to find it. You can use whatever you like, okay? But everybody should find these. I'm going to start with 36. Who would like to tell me the first two branches of theirs? Go ahead, Paige. So you're going to use 6 and 6. Can we use 6 and 6? Yeah, but can we stop at 6 and 6? No, why not? Because they're not prime, right? We've already done 6 or 36. 2, 3, 2, 3. And then we write it out. 2 squared times 3 squared. Easy peasy lemon squeezy, right? Okay, let's do 120. Most of you, hopefully, will choose 10 times 12 is what most people choose because there's a 0. But let's go with yours. 3 times 40, right? 30 times 4. Okay. Can I stop on either of those branches? Why not? They're not prime. So break it down again. What do you want to break 30 down into? New person. You want to go 6 and 5? Cool in the gang. Can I stop on either of those? Yeah, which one? 5. So I'm going to circle it because that's a prime number. Now, I've still got 4 and 6 in play. Are they break-downable? Yes. Which one do you want to break down? 6. No, we'll go 6 because Linda gave us 6 and 5. So what's this, Linda? 3 and 2. So we circle because they're prime. And then 4, 2 and 2. Then all we do is count. How many 2s do you see? 2 cubed. How many 3s? 3 and 5s? Just the 1. Everybody cool? Now, the GCF, if you look back on your sheet from right before, if you don't remember, the GCF is everything common by the smallest exponent because we're looking downwards. Yes, we're looking for parts. So is 2 common? What's the smallest exponent that works with 2? 2. 2 squared. Is 3 common? What's the smallest exponent that works with 3? 1. What is 2 squared? 2 squared is 4. 4 times 3 is 12. So that is our GCF. Okay? The LCM, if you look on your page before, you have to count everything. And kids always say, well, why do I not have to count this 5 when I'm doing GCF? Because GCF, as Paige and I were discussing, are the parts of the numbers, yes? Is 5 a part of 36? No, so that's why we don't count it when we're looking for the parts. Everybody understand? 5 does not multiply into 36. It's not a factor of 36. Right there. It's the number we're working with. Okay? So lowest common multiple, we look at everything, but we only count the highest exponent. Because we don't need to count all these 2's over and over again, do we? So is 2 there? Yes. What's the biggest exponent now? 3. Is 3 there? Yes. What's the biggest exponent? 2. And we have to count 5 because multiples are working upwards. What's 2 cubed? 8. Times what's 3 squared? 9 times 5. 8 times 9 is 72. 72 times 5, I'm going to help you out so you don't have to get a calculator. 360. So that is our lowest common multiple. And we use these in data and planning and things like that. All right? Nothing changes. Doesn't matter what the numbers are. So I want all of you right now by yourself to make your, if you're comfortable, do this whole page. But I want to add a number down here. 35, 84, and sure, 70. So now there's going to be 3 factor trees there. I might. So if you're comfortable, do everything. If you're still a little, just make the factor trees for B, C, and D. Okay? Everybody good? Go. I got needle nose pliers. I got erasers. I got Post-its. I got batteries. I got highlighters. But I don't got Snow White out. Manjo. Sorry. Yes, now you could go to the washroom because I'm done talking. So can you.
That's what
No, you can't. And, ladies and gentlemen, I feel it only fair to warn you, I am rationing your leavings of the room. You may leave the room twice a week from now on. Twice a week. So plan effectively. Yes, Julius. No. It's starting next week. You may leave twice a week.
So today we have unlimited.
You're welcome to try me and see how that works for you. Paige.
Me and Carlos are doing a 45 and 75.
Yep.
Kind like the GCF.
Yep.
We also use, so like it's 3 squared, but do we use the 5 squared from the other one too?
Are you trying to find GCF or LCM?
GCF.
Then no. You only use...
This one's 5 squared.
Yeah, so you only use one 5, the 5 from 45, and one of the 5s from 75. Because you're looking for parts, right? Smaller pieces. Let me draw all the factor trees and then we'll go through them all. Okay? Because 18 we've already done. 9 and 2. 3 and 3. So that is 2 times 3 squared. 4 and 6. 2 and 3. 2 and 2. 2 cubed times 3. Yeah, I'm just going to do... There is B, the list, right? 2 times 3 squared, 2 cubed times 3. That looks like 23 times 3. 2 cubed times 3. 45 and 75. 9 and 5. 3 and 3. So it's 3 squared times 5. And... 2 of you can go. I said 2 of you can go. So that one is 3 times 5 squared. And then over here, we have 5 times 7. We have 12 times 7. 3 times 4. 2 times 2, and 70, 7 times 10, 2 times 5. And we have 5 times 7, 2 times 5 times 7, and 2 times 2 squared times 3 times 7. So everybody, regardless of whether you understand LCM and GCF yet, all of you should be able to write these lists. And if you can write those lists, it's just a matter of practice. All you have to do is practice. Once you have the lists, that's the skill. So now let's look at these. GCF. Are factors bigger or smaller than the numbers you are working with? Smaller. Because factors build up. Everybody understands that, yes? 2 times 3 are factors of 6. Because they are smaller, they multiply together to make 6. So I need to look for numbers that are smaller than 18 and 24 So I can't look at the bigger exponents. Because if I look at this 3, this guy can't cover it, can he? So if I'm doing GCF, I look at what's common and the smallest exponent, because I need smaller groups. Is 2 in both of them? Yes. What's the smallest exponent visible? 1. So 2 to the 1. Is 3 in both of them? What's the smallest exponent visible? 1. So it's 3 to the 1. What is 2 times 3? 6. And that makes sense. Does 6 multiply into 18? Yes, 3 times. Does it multiply into 24? Yes, 4 times. Good. Lowest common multiple. Multiples are bigger, right? Right? Multiples are bigger. So I have to count everything. 2 cubed. I don't need to count this 2 because this guy covers this 2. So I need 2 cubed. This squared covers this 3, so I need 3 squared. 2 cubed is what? 8. 3 squared is? 8 times 9 is? 72. And it's done. Everybody cool? Now those are easy ones because everything was the same, right? We're going to do another one where everything's the same here, but you're going to do this one. If you haven't done it already, do the GCF. Oh, I changed wrong color. Do the GCF and the LCM of these two, if you haven't done it already. If you've done it already, you get to relax for a moment while your classmates catch up. I don't see how you could do it differently, Linda.
I was looking at the wrong one. I thought you were on.
I'm on C. Okay.
I didn't write that.
Yep. What is the GCF here? 3 times 5. Why?
Because they're both the lowest.
Because I only got 1 3 and 1 5, so it's 15. What is the LCM? 3 squared times 5 squared. Because building upwards, I have 2 and 2. 3 squared is? 5 squared is? 9 times 25 is? 225. Is everybody good with two numbers that always have the same factors? Can everybody at least vaguely see how to do A, B, and C? Because they've got the same numbers. It's pretty easy to work with, right? Now, let's look at D, and we're cool. We can do this. It's no problem. GCF. I need the parts for both of them. Is there a 2 anywhere in 35? So can I count these 2's? No, because 2 isn't a part of 35. Is there a 3 in 70 or 35? There's no 3. So can I count that 3? No. Is there a 5 in 84? So can I count that 5? So what's the only thing that's all the way through? 7. That's my GCF. Now my LCM, I have to count everything, but I only need to count it once. So do I need to count these 2's? How many 2's? 2 squared. Do I need to count this 3? Yeah, because I got to count it because it's going upwards. Do I have to count these 5's? How many of them? 1, because that's the biggest exponent. Do I have to count these 7's? How many of them? 1, because that's the biggest exponent. 2 squared is what? 4. What's 4 times 3? What's 12 times 5? 60. And what's 60 times 7? 420.
Okay, close enough.
Close enough. Does everybody see? Now, what if I gave you 6 numbers to make a factor tree? Then I'd have 6 of these, right? And I would just count what was common for all of them for the GCF and everything for the LCM. But we'd only count them once. Now, on the next page is some big numbers. Listen to me. Is making a product of prime factors for a giant number any different than making the numbers we've already done? No. It's exactly the same thing, isn't it? If you could do it on the previous 4 examples, and you could do it on A and D, say, and you get it right because the answers are on this page, do you really need to do all 6 of them? Do you? It doesn't change, does it? Okay? GCF. If you could do it with the little numbers and you get it right with one of these, and I would suggest you try a group of 3 and a group of 4, do you need to do all 4 of them? No. Because math is the same. But who is the judge of if you are actually doing it right? You are. So you decide. You are young adults. You decide how much of this practice you need. But if you stop at 1, 1, 1, 1, and you got them all kinda, are you really ready to prove to me you know what you're doing? No. And if you don't prove to me you know what you're doing, what do I give you for a grade? A poor one, right? The more you know when you are ready, that's when you can stop. Okay? Does everybody understand? Now, 13 and 22 are word problems. The answers are over here. Don't peek at the answer. If you're smart, you'll cover them up at home when you do these. Word problems, every kid has trouble with word problems. Just think about what it's asking. Are you going to be, if you are dividing numbers smaller, are you looking for a GCF or an LCM? It's 50-50. One person said LCM, one person said GCF. Smaller is GCF because I'm looking for the parts. If you're going to have more, then you must be looking for LCM. So just read the question. If the question is asking you to divide something up, GCF. If the question is asking you to fill something up, LCM. Page.
If it doesn't have an exponent, but you still need another one, do you take the biggest base for the LCM? Or do you
I'm going to come back and talk to you because I'm not sure what you're asking me. Okay, I'll be right there in 1 second. I just want to stop the recording. Yep. Everyone's cool to start? Go.